Assalamualaikum. My name is Nur Akila binti Ahmad Zawawi. We are from Group 9. Today we are going to explore a dynamic model of representative process, the fed-batch bioreactor. Fed-batch bioreactor is a type of fermentation vessel that cleverly combine the best feature of batch and continuous system. Think of it as starting with a simple batch operation. You inoculate the cell into a feed amount of medium. However, as the culture grows, we begin a process of feeding. That's where the continuous feature coming in. It starts like a batch process but then involve a continuous. The feed is added over time, but no output is removed during the operation.
Hi, Assalamualaikum. My name is Nurin and I will explain about the fed batch reactor process. In the fed batch bioreactor, the process begins just like a normal batch reactor. The vessel is filled with a nutrient medium and inoculated with microorganisms. The agitation and aeration start immediately to mix the culture and provide oxygen for the growth. As the cell grows, the nutrients in the medium begin to run out. So instead of letting them run out, a controlled feed system containing fresh substrate is pumped into the reactor. This addition is either continuously or gradually, which causes the reactor volume to increase over time. Because of the feed is carefully regulated, the substrate concentration inside remains low. This is important because too much substrate can cause inhibition or unwanted byproducts. Meanwhile, the biomass keeps increasing steadily as the microorganisms use all of the nutrients. Throughout the process, sensors continuously monitor the main parameter, which is pH, temperature, and dissolved oxygen. Each of these variables is automatically controlled. pH is adjusted by using acid or base, temperature is by cooling jacket, and the dissolved oxygen is by varying agitation or aeration. At the end of the process, when the biomass or product reaches its target concentration, the feeding stops and the culture is harvested. This method allows a high cell density and productivity, making a fed batch is the most common operation mode in the industrial fermentation and the biopharmaceutical production. Next, I will explain the difference between batch, fed batch, and CSTR reactor. A batch reactor is a closed system. The reactor is loaded at start and no material enter or leave during the operation. The process runs until it's complete and then the product is harvested. Batch is more controlled and simpler, but the productivity is limited. Next, a fed batch reactor starts like the batch reactor, but it includes a feed stage. The fresh nutrients are gradually added without removing its culture. This lets the operation control in the environment dynamically, preventing nutrient inhibition and extending the productivity phase. It is semi-closed and highly flexible. Next, for CSTR, the other hand is open. Fresh medium flow while the culture broth flow out at the same rate, keeping the volume constant. It operates at a steady state, providing continuous product output. However, it requires very tight control and can lose cultural stability if it disturbed.
Hi, my name is Aisha Nabila binti Mayazi. So for this slide, I want to present about the equations above in fed batch bioreactor. So as you can see in the diagram, it is a third tank where we continuously feed a substrate but can remove the product or cells during the process only until the end. To model this system, we use classic model equations to describe cell growth. For equation 293, defines the rates of cell growth as the specific growth multiplied by the cell concentration. Next, the equation 294 gives us the specific growth rate. It's dependent on the maximum growth rate, the substrate concentrations, and the monod constants. This shows that cell growth is limited by the amount of substrate available. Before we develop the mathematical model, we must make several simplifying modeling assumptions. This allows us to convert the complex reality of the bioreactor into manageable equations. For the first point, we are focusing only on the exponential cell growth stage, where growth is most predictable. We assume the fed batch reactor is perfectly mixed, so concentrations are uniform throughout. The third point, we assume isothermal operations, meaning the temperature effects are small and constant. Next, the liquid density is constant. Crucially, we are treating the heterogeneous mixture of liquid and cells, like the broth, as a homogeneous liquid for simplicity in our mass balance. Finally, as we just discussed, the rate of cell growth is defined by the Monod equation. Continuing with our assumptions, we define the product formation rates. The rate of product formation per unit volume is related to the cell growth rate through the product yield coefficients, as shown in 295 and 296. This coefficient represents the mass of product formed per mass of new cells formed. We also assume the feed stream is sterile, meaning it contains no cells. These assumptions lead us to the general form of each balance shown in 297. This fundamental equation is the basis for all the component balances we will develop next. Using the general balance equation and our assumptions, we can now write the individual component balances for our fed batch reactor. The cells balance 298 shows accumulation is only due to the formation rates since there is no cell inflow or outflow. The product balance 299 is similar. The accumulation is due to the product formation rate. Then the substrate balance 100 is more complex, where the accumulation is from the inflow minus the amounts consumed for cell growth and product formations. Finally, the overall mass balance 101 is simple. The change in reactor volume over time is equal to the flow rate as we have assumed constant density.
Hi, my name is Ainus Nisa binti Ismail, and I will talk about the control aspect and conclusion. In a feed batch bioreactor, the most important thing we need to control is the substrate concentration inside the reactor. To do this, a sensor monitors parameters like the substrate level or pH. This information is sent to the controller, usually a PID controller. If the value is too high or too low compared to the set point, the controller will send a signal to the feed pump to either increase or decrease the feed rate. This control loop helps prevent substrate inhibition, which happens when too much feed is added, and it also avoids nutrient limitation when the feed is too low. So, effective control ensures that microorganisms grow at an optimal rate and reach increased productivity. Feed batch reactors are widely used in the various industries. In the pharmaceutical industry, penicillin is produced using a feed batch mode to avoid high sugar level that can stop antibiotic production. In the enzyme production, controlled feeding helps maintain an ideal environment so that microorganisms can continuously produce enzymes. In the food and beverage industry, feed batch is applied in the yeast fermentation process like the bread making and fermenting beverages to ensure that the sugar is applied slowly and the yeast is not stressed. So, overall, feed batch allow industry to maximize yield while keeping the process stable. In short, a feed batch bioreactor is a hybrid system that combines batch and continuous advantages. The main focus is controlling the feed rate, to keep the substrate at the right level. This control improves microbial growth and overall process performance. That's why feed batch is widely used in the pharmaceutical, enzyme, and the food fermentation industries. It helps increase the yield and make the process more efficient.